Alright, for my question, it said, write and explain the mechanism for the reaction that occurs when 2-bromo-3-methylbutane is gently heated in 2-propanol. Show all the arrows, lone pairs, and any formal charges that may be present. Well, from this question, we know that we have an alkyl halide since the bromine is present, and that 2-propanol is an alcohol and will be playing a part as well as heat. We know that oftentimes when heat is introduced, elimination is favorable, but since it says slightly heated, SN1 may be possible. We also know that in polar protic solvents, example, water and alcohols, any solvent with OH really, that the nucleophilicity increases as you go down the periodic table. So our 2-propanol will be crucial. At first, what confused me though was when I ran through this problem a few times, I was stuck on whether to carry out as an E1 reaction or as an SN1. I did realize though that SN1 and E1 reactions typically go hand in hand and are difficult to dissociate between. They are very similar in characteristics, and the conditions that favor one also favor the other. We've already learned the characteristics of SN1 reactions and the factors that favor them, but we can also extend that to E1 reactions as well. So below I listed just a list of things that are similar between the two. They're both multi-step processes. They occur with the formation of carbocation intermediates in the rate-determining step. They follow first-order unimolecular kinetics. They're also sterically hindered substrates. They typically have a weak neutral small nucleophiles and heating involved, and they have moderate to high polarity solvents. But also, again, found that heat prefers the elimination reactions, but I just want to emphasize that since it says slight heat, that SN1 is still possible. But it is important to note that elimination would predominate due to the addition of heat. But SN1 will occur, and the SN1 mechanism leads to the substitution products, and E1 mechanism leads to the formation of alkenes, which is the double bond. So on the left-hand side of your screen, you're going to see the elimination problem. First, I'll carry this one out. So firstly, for an elimination reaction, it is a type of organic reaction in which two substituents are removed to form a molecule. This is two-step, and it's known as E1. So since this is a secondary halide, it is also a relatively faster reaction time, which is why only slight heat is required with the 2-pentanol. The rate is proportional to carbocation stability. Tertiary, secondary, and primary. The third degree, which is the tertiary, is the one that is most stable and favorable. First, the leaving group, which is in this case is the Br, leaves, leading to the formation of this carbocation. Since the 2-propanol is a polar protic solvent, which means it's a hydrogen bond donor, the carbocation will form in the first step and will undergo rearrangement to get better stability. This is known as a hydride shift. This is when a hydrogen atom in the carbocation migrates to the carbon atom bearing the formal charge of +1, which is carbon 2 in our case from the adjacent carbon, carbon 1. As has been mentioned before, commonly used solvents in SN1 reactions are water and alcohols. They frequently also double as nucleophiles. But in E1 reactions, these same substances would act as a basis to capture a proton in the elimination step. So after our hydride shift, the lone pair of oxygen from 2-propanol abstracts the H atom to form a double bond. This then leads to our product, which is 2-methylbutene, which you see in the bottom. Alright, for our SN1 mechanism, you're going to see that on the right-hand side of your screen. SN1, as I've mentioned kind of before, are again fairly similar to the E1 elimination mechanisms. These ones are nucleophilic substitutions involving a nucleophile replacing a leaving group. However, SN1 reactions are unimolecular. This means the rate of the reaction depends only on the concentration of the reactant. For this reaction, we again see the quick formation of the carbocation. Bromine again leaves the molecule to create a secondary carbocation, which is very similar to the one we saw before. From here, a hydride shift takes place once again, which leads to the rearrangement of the adjacent carbon to create a tertiary carbocation, which is incredibly stable. Again, it's important to note that whenever there is a possibility of forming a more stable carbocation, the molecule undergoes rearrangement to do so, which is otherwise known as a hydride shift. Next, in this step, the nucleophilic 2-propanol attacks the tertiary carbocation via the lone pair of the OH group, which ends up in leading us to the formation of our product when the proton is lost to produce the final product. You can see on your screen how the propanol attaches quite well, and then you see the H group leave, causing our product to look as it does. And lastly, I just want to wrap up by showing that E1 side that's on your left-hand side is showing how that product ends up being a double bond. That right-hand side shows that SN1 reaction, which shows how that 2-propanol attaches, which creates that product that we see. And although these have fairly similar steps, they do end in different products. And this answers the question for write and explain the mechanism for the reaction that occurs when 2-bromo-3-methylbutane is gently heated in 2-propanol. Show all arrows, lone pairs, and formal charges that may be present.